Okay, so let me give you an update. Hello there, and welcome to more physics. So I've been in the process of kind of building up examples of using the momentum principle. I did the case where I was dropping a ball. You know, go back and look at that video. I modeled that. I did a numerical model for that. And now I want to do the model for a mass on a spring. So today, I'm really just going to do two things. I'm going to find the force due to a spring. And a real spring. Actually, it looks a real spring. See, there's a spring? And then I'm going to oscillate a mass on a spring and talk about why that's a difficult problem. And then in a follow-up video, I will then model the motion of a mass on a spring. Are we cool with that? Okay, I got a little bit different camera setup here, so if something weird happens, I'm going to blame the setup. Okay, that is the start. So here I have a spring. It's kind of hard to see. I should probably zoom in, but if I had like a zoom in control thing, that'd be cool. Zoom in, you can see that. Zoom out, you see me. But so the nice thing about a spring is the more you stretch it, the harder it pulls back. Okay. So I'm going to collect data on this spring. So let me just start off with a measure of a couple things. I'm going to write down a couple things. Let's put this right here so everything's stationary. Slide that over. Okay, so I have my holder is right here at 46 centimeters. I'm not going to be exact. I'm just going to be approximate. So here I have this. This is at 0 centimeters, and this is at 46 centimeters. And then I'm going to always measure from the bottom of the coil part. So that's at 41.8. And everything's in centimeters. I'm not going to write centimeters. And I'm going to write this down in just a second. Okay. So now let's take this mass. It says 20 grams. I'm going to hang it right there. And so it's stretched down. So now it's stretched down to 40.3. So at that point, the mass is at equilibrium. So if I drew the forces on that mass, I have the spring is pulling up, and the gravitational force is pulling down. And those two forces are balanced. They're equal because that mass is in equilibrium. So the net force in that mass has to be 0. So that means if I know this gravitational force pulling down, then that would have to be the magnitude of the spring force pulling up. Okay, so that's what I need to write down. So this is let's write that as 20 grams. And that's 0 grams. Okay. Let's put some more mass on there. Let's just see if I can write these things down. And then I'll put it on the computer. Okay, what if I take this mass, 50 grams. And I could do a whole bunch of data here, but I'm going to make it as simple as possible. Maybe 5 data points. Okay, so this hangs down to 36.1. And that's 50 grams. Okay, now let's see, I could do these two together. That's 70 grams. 31 to 30.4. 30 to 33.4. Are we having fun? Okay. Let's do another one. This is 100 grams. So this is 29.5. I'll write it over here. oh, right there, 29.5, 100 grams. Let's do 120. Let's see, so that's 1, 2, 3, 4, 5, technically 5. This will be my last one. I'll put it down here. So that's going to be 26.5. 120 grams. I think that's going to be enough data. I mean, definitely more data. If you're doing this for lab, do more data. Get more data points, but this is going to be enough for us. I do want one more thing here. Okay, so what I want to do is let's suppose I go back to 100 grams. And let's write this over here. M equals 100 grams. And I pull it down to, let's say, I'm going to pull it down to 27. Let's do 26. I'm going to pull it down to a y0 equals 26 centimeters. And I'm going to let go, and let's see what it does. Look at that. Okay, so it's oscillating up and down. That one, it kind of stopped. I'm going to move the meter stick. And we'll do it again. Now what I want to do is get the period, how long it takes to oscillate. And I'm not going to be right at 27, but I'll be approximate. So I'm going to take my phone, and I'm going to use my stopwatch. Stopwatch. There it is. Okay, I'm going to start it. I'm going to time, let's say, 10 oscillations if I can get 10. So I'm going to pull it down. And I want the time to go from here up and back down. I'm going to do that 10 times and divide by 10. Okay, so I'm going to get it started and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7.45. So I'm going to say the period, which I'm going to use capital T, is 0.745 seconds. That's for one oscillation. Okay. Okay. So now I want to. What I'm going to do is make a model for the mass, the force on the spring, and I'm going to switch to the computer. So I'm going to stop in a second. But let's talk about what we're going to do, and then it'll make more sense once I switch to the computer. So here is my complicated version of a force through the spring, and this is the model from Matter and Interactions, my favorite book ever, and you know who you are, the force through the spring. So if I have a spring right here, and it has some unstretched length L0, and then it's stretched over here. So this is, I'll call this the vector L. And yes, this is more complicated than it really needs to be for a lot of situations, but not for all. For some situations, I really have to do it this way. Then this is going to have a spring force going in that direction, and we'll write it as Fs negative K, the magnitude of L, minus the unstretched length. So this right here is the stretch, S. And then in order to make this whole thing a vector, K is a scalar, the magnitude of L is a vector, scalar, so that's all a scalar. I'm going to multiply this by L hat, so the unit vector in the direction of the spring, and this will give me a force. So you may have seen this, Fs equals negative Ks. That's bad, okay, but that's the same idea if I take away the minus sign, because now I'm dealing with the magnitude of the spring force is proportional to the stretch S and the spring constant K. So if I made a graph of force of the spring versus stretch, the slope would be the spring constant K. And so I'm going to get that force of the stretch by using the mass converted to kilograms and multiply by G 9.8 to get the weight, and the weight is equal to the spring force. And that's going to give me the spring constant. After that, and I'm going to do that. I should do that now, but I don't want to switch cameras. So after that, I'm going to consider how to model this motion. Let's just talk about that, and then I'll do this out of order. So suppose I have this spring and a mass. So here is the equilibrium position, and I pull it down. So I have the gravitational force mg, and then I have the spring force pulling up. And the spring force is greater. When I pull that down, my hand's on it, so I'm making it an equilibrium. But when I let go, I have a greater force pulling up than going down. And my momentum is 0. So what's going to happen? So now I have a net force pulling up, and I have 0 momentum. So that means that the change in momentum is up. So after a short little time, it's going to be right here. So now the spring force is less because it's closer to equilibrium, but now it's moving up. So the momentum is in the plus y hat direction. And it's going to keep on moving up until it gets back to here where the net force is 0, but now it's moving. So even though it's in a location where the net force is 0, it's already moving up, so it's going to keep moving up. It's going to keep moving up until this spring force is now lower than the gravitational force, smaller, and it's going to slow down because now the net force is down. And eventually it'll get to the part where it stops. But when it stops, it's not in equilibrium, so it's going to start moving back down again. So this is a tough problem, because if I use the momentum principle, F net delta P over delta T, that's cool, okay? Except that my force is not constant. My force depends on the position. So as this thing moves, I have a change in that force, and that makes this whole problem more complicated. And it's a tough problem to solve. Okay, picking up. So the video cut off a little bit at the end, but I think we're all good. We're all good. So here is the data. I have the data on the board behind me, and I'm going to put it in the spreadsheet, and I'm going to do a calculation, then I'm going to make a graph, and then we're going to end the video. It's going to be great. Okay, so I'm looking behind me, but the first thing I'm going to want to do, I have two things I want to put: the mass. Oops, I can't even type mass in grams, and the y position. Let's just put y position in centimeters, because that's what I wrote it. So the first is 0, and it is at 41.8. The next is 20, 40.3, 50, 36.1, 70, 33.4, 100, 29.5, and finally 26.5 at 120. Okay, so I want to plot, let's plot the force versus the stretch. So let's first calculate the force, and that's just going to be equal to this value. I need to convert this to kilograms, so it's going to be this divided by 1,000 times 9.8. 9.8 newtons, so that's 0, and then if I scroll down here, just copy that down. So the biggest is 1 Newton, that's fine. Okay, and then the stretch, S. This is a little more complicated because I need to first convert this value to meters. This is going to be 0. So this is going to be equal to, let's say this minus this, and let's put this as a dollar sign so the 2 doesn't change, and then divide that by 100 to convert it to meters. So that's, ooh, that's error. Oh, that's because I put the wrong, it goes right here. Okay. 0 meters. So this is the force in newtons. I'm not going to write down the units because I don't really care. Okay. Ooh. It should be the other way around. Should be this. And recopy. Okay, so this one stretched 15 centimeters. That seems cool. Okay, so this is the data I want right here. I'm just going to copy the numbers. I like to use Plotly to make graphs. So here's Plotly. No, that's not Plotly. That's Plotly. The one issue here is that I don't know how to do calculations in here, so I'm just going to paste that's why I'm pasting my data. And I'm not even going to make the name right now, so let's just add a trace. So the x value is going to be B, the y value is going to be A, and there's my data. You can't see the whole thing because I messed up. We can make this a nice chart, but I just don't really care about that right now. You see here it is indeed linear. The one thing I do want to do is add a curve fitting, add a fit, select an option, trace 0, linear, 1, 1, run. Right there. You see that it is indeed a linear fit, and it has a slope right here of 7.51. I'm writing that down. K equals 7.51 newtons per meter. And you'll also notice that the y-intercept is very close to 0, so that's good too. Okay, so this is a pretty good model. It's going to be good enough for us to do what we want, which is to make a numerical model for the motion of a mass on a spring, and it's going to be in this next video, and it's going to be awesome. The end.